Alright, so we're going to be learning in this video about the evidence behind the theory of evolution. And we're going to focus on the fact that the evidence for evolution comes from a bunch of different sources. It comes from things like geology and geography. It comes from sciences like the physical sciences and the chemical sciences, and it even comes from mathematics. But before we really get into the idea of the evidence for the theory of evolution, I want to talk about that word. I want to talk about the word theory, because this is something that people get wrong all the time. Most people think a theory is kind of like a hypothesis, which means it's a guess. And that's not actually true at all. In reality, a theory is something that is supported by large amounts of evidence. A theory has to be tested again and again and again by many different scientists studying different disciplines all across the world in order to become a theory. Now, part of the reason people get confused is they think that if a theory was good enough, it would one day get turned into a law. They think theories are like kind of questionable, but laws are certain. And that's not true. Laws and theories are actually pretty much the same thing. The only difference is that laws can be represented with math and that theories are not. So Newton's laws are laws because you can write equations for them, like force equals mass times acceleration. If you couldn't write equations, they'd be Newton's theories. The theory for evolution will never become a law. It's actually as good as it's going to get, and it will always be the theory of evolution. It's going to continue to change, but for the most part, we are very certain about the theory for evolution. And so we're going to talk about why we believe this theory of evolution and what the evidence is. We're going to start with geology and geography, and I'm going to introduce that by giving kind of a weird fact. Did you know that all of the alcohol sold in the United States, by law, must be radioactive? That's right. It has to be radioactive. If it's not radioactive, you cannot sell it to people. So the question is, why is that? Okay? So in order to understand why that is, we need to realize that alcohol is really just a chemical called ethanol. So that's the molecule right there. It's got two carbons, one right there and one right there. Those are carbon. And it's got one oxygen right here, and everything else is hydrogens. And that's a pretty simple molecule. So instead of making it by taking grapes and smashing them and then putting yeast in there and fermenting it like you do when you make wine, you can just make ethanol in a lab. You could make it out of, say, oil, just like we make gasoline out of oil. And there would actually be no difference. Ethanol produced in a lab would be pretty much identical to ethanol produced in a normal winemaking process. It would affect a person exactly the same way, and it would probably be cheaper to make. So why don't we just make all the alcohol in a lab? Well, it turns out that basically farmers don't like that. If you're a guy who owns a wine or a vineyard and you make wine as your living, you don't want a bunch of scientists coming in and stealing your business. So in the United States, we made laws to protect people who make beer and wine and liquor the natural way. And so we had to figure out a way to determine if alcohol was made naturally or if it was made artificially. And the key to knowing if it's natural alcohol or artificial alcohol is whether it's radioactive or not. See, the way it works is that if you have a plant, it is always bringing in, we could say breathing in, even though it's not really breathing, but it's always drawing in carbon dioxide, CO2, from the atmosphere. Now, the carbon in this CO2 is naturally radioactive. That means that that carbon, some percentage of that carbon, just going to pick a number, this is not realistic, but let's say 20% of that carbon is what we call C14. That's carbon with a few extra neutrons. And naturally, that carbon will lose those extra neutrons and become C12. When it releases those neutrons, that's what radioactivity is. It's when little particles fly off of an atom naturally. So CO2 that's in the air has a certain percentage of C14 that releases neutrons all the time. When the plant absorbs that, it becomes carbon in the plant, and that carbon is also radioactive. And as long as the plant is alive, it's going to keep bringing in CO2, and it's going to remain pretty radioactive. Now, if that plant one day, that tree gets chopped down, now that it's dead, it's no longer going to be pulling in carbon dioxide. And so whatever C14 is in it, let's say it's 20% when it first dies, is going to steadily turn into C12. And so the longer that plant has been dead, the less C14 it will have. Okay? And so what we figured out is, if you want to figure out if your alcohol is natural or artificial, you check if it's radioactive. If it's radioactive, that means it came from a living plant like this one. Whereas if it's artificial, that means it came from materials that were not living. And so it won't have any radioactivity in it. That's why all alcohol has to be radioactive, so it comes from living plants. Now, we also use this technique for something else. We use it to figure out how long ago things died. So one example of radioactivity that's a little bit different would be potassium-40. Potassium-40 naturally decomposes into argon-40. It actually loses a proton or a few protons rather than neutrons. And it takes about 1.3 billion years for, let's say if you had 20% potassium-40, which is K40, it would take 1.3 billion years for half of that potassium to turn into argon. So 1.3 billion years later, you'd have only 10% K40. Okay, so 1.3 billion years is the amount of time for half of that to disappear. That's called a half-life. And different chemicals or different atoms have different half-lives. So carbon-14 has a half-life of only 5,000 years. That means we can use the amount of carbon-14 to figure out how old something is up to about a few thousand years. So if it's something that's pretty recent, like an arrowhead that you found lying in the ground and you want to know how old it is, you'd look at the amount of carbon-14. If it's something older, like a dinosaur bone, you'd look at the amount of potassium-40, because that'll tell you how old the thing is to the billions of years, and so on and so forth. So what do we learn? This whole thing is called radioactive dating. So you're using radioactivity in order to figure out how old, sorry, that's an I-N-G, to figure out how old something is. So what does this have to do with evolution? Well, the result of radioactive dating, looking at all these different things, we figured out that the Earth is about 4.6 billion years old. And that's a lot older than we originally thought it was. People used to estimate that the Earth might only be 1 million years old, or maybe only a few 100,000 years old. And if it's only a few 100,000 years old, there's not enough time for life to have evolved from a little tiny single-celled organism all the way up to something as complicated as a squid or a whale or a human. But if the Earth has been around for 4.6 billion years, which is a really long time, then there has been enough time, so Earth is old enough for evolution to happen. That was one of the biggest complaints about evolution in the first place, was people were worried the Earth wasn't old enough for this to be possible. And radioactive dating told us it is. Another piece of evidence we can get is from biology, looking at the parts of animals. So if we look at the arm bones of all these different animals, humans and horses and cats and bats and birds and whales, we see that they all have basically the same arm bones. So you got one long bone up by the shoulder. On the horse it's a little bit thinner, but it's still there, or a little bit shorter. On the bat it's really tiny, but it's still there. On the whale it's like this little nub. But that same bone is present in all these different kinds of arms. And then beneath that, there are two bones in all of these, so on and so forth. All right? So they all have these same structures, but they're used for different things. Okay? So these are what we call homologous structures. So these are structures that are very similar, but they're used for different purposes. And what these tell us is that all of these animals had an ancestor that had these bones. And over time, that ancestor evolved to take advantage of all these different environments, whether it's the ocean, like the whale, or the air, like the bird and the bat, or running really fast on the land, like a horse. And so they took those basic bones, and the shape of them changed over time through evolution into something that fit their environment. And probably the craziest example is the hand. The human hand is built for grasping, whereas the bat hand, much longer and thinner and lighter, is built for holding a wing out and flying. The weirdest one is the horse hand. Horses have, technically, 5 finger bones, just like a human, but one of them is super long. This is basically the horse's middle finger, and the hoof of a horse is basically the horse's fingernail. So horses have evolved so that they have one really long finger that they run on. And that's how all hoofed animals are. So these are examples of homologous structures. Once again, that's evidence for evolution. We can also look at the chemistry of living things, and we can look again at homologies. So these are things that are very similar, but for slightly different purposes in different animals. And we can look at them for molecules. So a common molecule that we'll look at is the hemoglobin molecule. Hemoglobin is what carries oxygen in your blood. And if we look at, hemoglobin has about 60,000 individual pieces that make it up, and each of the pieces is called an amino acid. Okay? Now, what this graph shows is the number of differences between human hemoglobin and, let's say, a rhesus monkey. So a rhesus monkey has 5 amino acids that are different from the human. 5 out of 60,000. So rhesus monkey hemoglobin is almost identical to that found in humans. A mouse's hemoglobin has 25 amino acids out of 60,000 that are different from a human's. So this tells us that monkeys and mice are closely related to humans, but that a monkey is more closely related than a mouse. And we can go down this list and see all those differences. But even something really weird, a fish with no backbone, like a lamprey, has only 125 differences in its hemoglobin. So we're still pretty similar even to the lamprey. And so this again shows us the pattern of life evolving to fit different environments. And it can tell us the story of how we're more closely related to some things than to others. And all of that provides evidence for this story of life starting out as a few organisms and branching out over time to fit all these different environments across the world at different times.